Thanks so much, Omar. When Omar invited me to be here today, I was really pleased because, like Al Gore, I really genuinely believe that it is groups like this, it is innovation, particularly social innovation, that is going to be central to creating a better society into the future. And that includes dealing with the climate crisis and a whole lot of other issues that beset us. We're not seeing the action we need from government. Not-for-profits like the Climate Council do good work, but we desperately need that energy and solution solving that comes from joining science and innovation with new social models to create something very different from what we have today. So what I thought I'd do today is really focus on one aspect of the problem that we face, the future that we face, and that is around our relationship with planet Earth, and particularly as that relationship is mediated through a series of figures, through the carbon budget and through the technologies that we already have to hand and some that we can see on the horizon that might change that relationship a bit. I've called it, just to be provocative, I've called the presentation The Governed Planet because it recognises the role of us humans as the sort of mind over the land, if you want. We are so powerful in so many ways now, we're influencing so many aspects of the Earth system and of biology that we need, I think, first and foremost to recognise that relationship and the centrality of ourselves in terms of the processes. So just to remind you, and I know there's some high school students here in the audience, climate change is not a new science. This man here, John Tyndall, back in 1859, used that antique-looking machine there to measure the heat-trapping potential of carbon dioxide. And that set in motion a whole series of inquiries, including by Tyndall himself, on how CO2 levels in the atmosphere may affect the temperature, the surface temperature of the planet. And over the decades since that foundation work was done, we have... here we go, thank you. We have developed a series of climate models which have been very, very influential in terms of telling us how we are affecting the average surface temperature of the planet. What you see here is a series of graphs that look at temperatures through the 20th century. So they're really a historical data set. We know that black line through each one of those graphs for that region of the planet is the actual temperature that occurred through that century. And there's two lots of modelling there. The purple kind of zone, if you want, represents a computer model that is fed all of the information about the way Earth's temperature is arrived at the surface, except the human influence. And the red area is exactly the same computer model. Sorry, I don't know what happened there. Exactly the same computer model with the human influence put into it. And you can see that the historic data is only consistent with the modelling if you include our influence, our human influence. This is how scientists know that we are influencing the Earth system. So we are responsible for many changes. That work has, in recent years, or in recent months really, been given a much finer point. Earlier this year, scientists published the Anthropocene equation. You can see it there. It lists the factors that affect the Earth system historically and today. And you can see that over the last 40 years, a big new factor, humanity, has to be factored into that equation. What we are now doing, this equation tells us, is driving the Earth system, the temperature-related part of the Earth system, at a speed 170 times greater than the natural forcing factors that change the climate. So we are accelerating climate change in a way that the natural factors simply cannot do. We are causing very big changes in the Earth system. Is that? I think the battery might be dying on this. So why is all of that happening? Basically, what we as humans are doing is pumping a lot of material from the Earth's crust, combusting it and putting it into the environment. This Steve Haley is an artist, an Australian artist who does digital artwork. He buys these images from gaming shops as files and puts them together in these rather beautiful artworks, but he's also a very rigorous, he takes a very rigorous approach to his science. And what he's done here is illustrate the number of barrels of oil that are extracted from Earth's crust every second of every minute of every hour of every day. And you can see there, you get a sense from looking at this art of the scale of our enterprise in terms of extracting things from Earth's crust. Add to that the coal, add to that the natural gas, and you get a sense of how big this change is. So, there we go. So where is this carbon going? It's helping us do a lot of good things. We run our industry with it. We heat our houses with it. We grow our food with it. You can see here where it's all going to. The key figure that I want you to look at in this graphic, though, is that one in the middle of the circle, 49 gigatons of CO2 or equivalent per year being put into the atmosphere. How big is that figure? Well, you can ask, how many people would we need to put into the atmosphere to get that mass? You would need to put humanity twice over into the atmosphere to get that mass. It is enormous. If you wanted to take out, say, just 10% of it, just 5 gigatons, by doing something sensible like growing trees, how big an area would you need to plant to forest to do that for just 10%? Has anyone got any idea? You'd need to pretty much cover the contiguous 48 states of the USA in forest and keep them growing vigorously to take out just 10% of what we put in every year. So we're dealing here with very, very big numbers. Can I, perhaps you could help me with the thing. I kind of reluctantly put this slide in. I hate blaming other countries, but it gives you an idea of the contribution of greenhouse gases. Australia's down towards the bottom of that list, 1.5% or thereabouts of global emissions. It's often used as an excuse by people for inaction. The fact is there's 193 countries that all contribute small amounts. We all have to work together to solve the problem. You'll see China at the top there. It's not really fair to blame them. I think if we took away everything that was made in China from this room, some of us may be quite embarrassed at the end of the day. We might find we've got nowhere to sit on and no clothes to cover ourselves with it. They manufacture, China is the world's manufacturer, yeah? It does stuff on our behalf. So this is a global problem. We all have to work together to solve it. How is this warming affecting the planet? Scientists have determined that every ecosystem on Earth is being affected by this warming. You can see a few examples there. Could I have the next slide? Just to reinforce that point. So some of the worst affected elements are the world's coral reefs. We've seen the Great Barrier Reef this year and last have 2 back-to-back bleaching events for the first time ever. It's had a profound effect on the reef, killing somewhere between 22 and 30% of the coral. In 2012, half the coral was already dead. We've now killed an extra 20-odd%. Coral reefs don't cope well with these changes. And when you think about it, there are good reasons for that. I mean, if you create an underwater heat wave and warm the water, things living in the water that can't move have very few options. On land, we're used to being able to sweat or to get into the shade or get into a breezeway. Corals can't do that. Marine organisms can't do that. So underwater heat waves are very dangerous. They cause bleaching and then the death of the corals. And they're not alone in terms of the impact. The alpine ecosystems globally are under threat. You may have seen it in the paper just today, impacts on Australia's alpine ecosystems of the warming. These 2 animals here are tree kangaroos. They're some of my favourite animals. In a past life, I was doing work in New Guinea. I named both of those tree kangaroo species. They're both restricted to alpine summits high in the mountains of New Guinea. Their habitat probably includes about 1,200 metres at most. For the little one, the white-faced one is much less than that, on top of mountains. We know that for every degree of warming, the tree line rises 300 metres in New Guinea. We're looking down the barrel of 3 degrees of warming by the end of the century, which means that these things just won't be there. And not just those beautiful animals, but their entire habitat, all of the species around them. And this is one island in one part of the world. Magnify that by the planet and you get a sense of the loss and disruption that this warming will cause to alpine ecosystems. We know that the oceans are being profoundly affected, not just the coral reefs. This is just a basket of fish that you might fish out of the North Atlantic as part of a commercial fishery any day of the year. And they are shrinking. If I could have the next slide. As a result of warming. As the ocean warms, there is less oxygen availability, there's less food availability, and fish are shrinking in size. So that little basket of fish has shrunk on average by about 23% over some decades. So our food is being impacted. Thank you. Wine is, that industry is really in the front line of climate change. The conditions to grow the sort of grapes that are required for fine wine are so precise that small shifts are very dangerous. I've done some consulting with the wine industry in the southeast of South Australia, where they tell me that Veraison, the moment they harvest their wine, has advanced about a month. And they are seeing now unprecedented pressures on their wine growing, resulting from climate change. Heat waves are causing grape growers now to develop and formulate sunscreens for their grapes. Otherwise, the grapes get burned. This is something new for the industry. They haven't had to do it before. They also are suffering from smoke taint. As bushfires become more extreme and larger, smoke travels long distances, and smoke-tainted grapes are useless for making wine. So another big risk factor there. Some wine growers are moving south. They're abandoning their vineyards in the northern hotter areas and moving to places like Tasmania. Others are growing new varieties of grapes that are more tolerant of the warm conditions. Thank you. Food security is also at threat. Grains particularly, C4 grasses. Carbon dioxide is a fertiliser effectively to these plants. But because they grow more rapidly, they have the proportion of protein and minerals in the grain, so the nutrients in the grain, is reduced. And this is such a concern that China, just 2 years ago, ran a front page headline in their paper, the China Daily, saying climate change threatens China's food security. These are big issues for coming decades that we need to address. Can I have the next? So we have made some progress in terms of dealing with this juggernaut of problems. The Paris Agreement was a foundation stone, and Al Gore, by the way, played an exceptionally important role in brokering the Paris Agreement. It was he that worked with the Indian government to make sure that they were in a position to be able to agree to this, which was difficult for them. But the Paris Agreement is a real foundation stone. The problem we face is it's coming very, very late. That there's already a lot of gas in the air and more coming in every year, 50-odd gigatons every year. Can I have the next slide? Which brings us really to the carbon budget. What position are we in at the moment? Now you can see there a very rough kind of sketch of the carbon budget. You can imagine all those barrels of oil coming out of that black stuff there under the ground, going into the atmosphere. Some of the carbon, thankfully, is captured by the natural processes of our planet. A lot of it disappears into the oceans. Some of it is absorbed by growing plants on land. What remains is the stuff that floats around in the atmosphere and causes the warming. Now, in terms of the carbon budget as we formulate it, and the IPCC scientists formulate it now, could I have the next slide? They assume that those sinks are stable and unchanging. Recent science has shown that that is not the case. As the Earth warms, bacterial activity in soils, for example, increases, and the soils hold less carbon. As the ocean warms, it's able to hold less gas and therefore less carbon. So Earth's carbon sinks are weakening very substantially. That set of figures there, don't try to strain your eyes reading them, but you can think about them telling us this, that we thought we had a bank account perhaps with $100 in it at the bank. So we go and see our bank manager and he says, "Oh, I'm sorry, fees and services have eaten into your savings there and you've really only got about $70 left." So we have less carbon budget than we thought because the sinks are weakening and over time will absorb less carbon. Therefore, more will stay in the atmosphere. So we can have the next slide. But that's not the end of the bad news for our budget. We are not currently accounting for methane and nitrous oxide in the carbon budget, about 16-17% of global warming potential. And we do it for a good reason, that those gases, their warming potential is offset by particulate pollution, that shocking stuff you see over China and India that make the air unbreathable. China and India are moving very fast to clean up that pollution. So in years to come, we will have to include that warming in our carbon budget. Now, to do that is really the equivalent of going to the bank manager and him saying, well, sorry, we thought you had $70 in the bank, but there's been some sort of fraud going on, and actually you haven't got anything left. In fact, you owe us some money, right? And that's, we think, the science is still not absolutely firm on this, but we think at the moment that we may be some gigatons in deficit in terms of staying below 2 degrees. We will get a better grip on this in coming months as new science is published, but we certainly don't have the scale of carbon budget that we thought we had some years back. Sorry. So this is some work in progress which just summarises that work. This is saying we are 10 gigatons in deficit. Thank you. Could I? Now, as Al Gore said, we are making great strides when it comes to reducing our emissions. Wind and solar are booming. They're great new industries, and they will eventually displace fossil fuels. But I have been aware for a number of years now that doing that is just not enough. It is the burden of greenhouse gases in the atmosphere that are the problem. And in 2007, I was invited by that man there with the beard, not Al Gore, the other one, to come to his island in the Caribbean to address his group. But it was interesting. I literally was walking along the street, heard the phone ring, picked it up, and this voice said, "It's Richard here. Would you like to?" I said, "Richard? Oh, yeah, right. Would you like to come to my island to talk to my group, virtual group?" I said, "Oh, that Richard, right? Yes, yeah, sure." So he flew me over there, and I was then chair of the Copenhagen Climate Council. We were working to what we hope would be a successful COP15. So I made a presentation to the group. And Richard, at the end of it, said, "You know, I deal with people all the time. I'm an entrepreneur. I know what people want. And I don't think that we're going to solve this problem with the current tools we have." He said, "I'd like a backup plan. I would like to, and in order to do that, I'd like to put a prize out there for people who can draw carbon out of the atmosphere, because I think we're going to overshoot." So we established the Virgin Earth Challenge. Al Gore is one of the judges. I'm one of the judges. James Lovelock is another one. And Sir Chris Minterkel's the fourth. And we look at technologies that they submit applications to the challenge that have the potential to draw 1 gigaton of CO2 out of the atmosphere per annum. Very, very big figures. There's been 11,000 entries into that prize now. We're hoping we may give a prize in the next 12 months or so. But I have drawn huge inspiration from this. I realise that Richard was right. We didn't get where we needed to get to at COP15. It's taken us much longer. The pollution stream has grown faster. So we desperately need that backup. So my last few years have been all around trying to energise innovation behind those technologies, because we need them. They're barely on the radar now for people, but we will not stay below 2 degrees without drawing some of the gas out of the air. Another way of thinking about that is that gas in the air is sort of money in the bank, yeah? We know the scale of it. We know what it'll do into the future. We know how long it lasts. We know we're going to need to get it out, and there'll be a cost involved at that, or some profit will be made as we do it. So the rest of the presentation is around those opportunities that exist in getting that gas out of the air. Could I? So there are basically 2 ways of taking CO2 out of the air at scale, a biological and a chemical pathway. Could I just run through the... So the biological pathway includes things like planting trees, very, very useful, very important, but for reasons I outlined earlier are not going to solve the whole problem. The Earth just isn't big enough, the land surface isn't big enough to do that, and there's lots of pressure on it already. Soil carbon is probably 3 times, there's 3 times more soil carbon than there is carbon in a living biomass on land, a very important repository, but again, the scalability is an issue. So we can do it that way. Can I have the next? The oceans, however, offer more opportunity, and I'll come to that later. The oceans are 72% of the Earth's surface. They're full of fast-growing plants. They offer some real opportunities. Could I just go on to the chemical pathways? We can have, I think that's direct air capture. I can't see from here, is it? Because someone confirm for me, my eyes aren't good enough. I think it is. So we can capture CO2 directly from the atmosphere using various processes. And it's very interesting. I've actually seen one of these plants, you know, the direct air capture plant I saw in Canada was probably the size of this room. It captured the same amount of CO2 as 1,000 hectares of forest. Very, very, very smart technology. We can make carbon negative concretes that can draw in CO2, or we can use silicate rocks. And silicate rocks are a natural part of the Earth's geology. They can be ground up, and as they weather, they capture CO2. So there's North America, just to reinforce that example of tree planting, the difficulties doing that at scale. Could I have the next? Seaweed farming, however, as I mentioned, is different. Seaweed grows 30 to 60 times faster than land-based plants, and because it's all the photosynthetic part of the plant. Could I have? And the ocean is a very, very big place. So there is potential there to use seaweed as a mechanism to draw down CO2 very rapidly. And we're not that far from the ocean here, and in this area you have one of the great innovators in the seaweed technology, Pia Winberg, who is working to do fantastic things in this space. So how much could we potentially do with seaweed, and how might it work? Could I have the next? A scoping study published in 2012 suggested that were we to take 9% of the world's oceans and cover them in seaweed farms, we could draw down all or more than all of our current emissions of CO2, so 53 gigatons of CO2. And when I heard that, I thought, fantastic. But not only that, we could feed the world with those seaweed farms, because when the seaweed draws the CO2 out of the oceans, it deacidifies the oceans and creates a great environment for growing anything that needs a shell, like oysters or bones, fish, whatever you want. So we could feed the world, and we could get the CO2 out of the air with seaweed farms. I thought, that 9%, I better check out how big that is. It's about 4.5 times the area of Australia. That's like creating a seaweed farm the size of Asia in the Central Pacific, right? Big. How would it, but let's yes, it's awe-inspiring to think of it. How would it work? The seaweed, in these conceptual approaches, grows on racks 25 metres below the surface, so out of the harm's way as far as shipping goes. Natural energy, clean energy is used to bring water up from 300 metres down, which is very cold and full of nutrients, to irrigate the crop. And the seaweed grows, you intercalate the seaweed with all of your protein, the fish and so forth you want. And when the seaweed is grown, you can cut it off and drop it into the ocean depth. Once it's down 1 kilometre, it's out of the system effectively. It's not quite like putting coal back in the ground, but on the timescales we're interested in, it's a similar sort of approach. So could we go on? As we think about this, we have to be aware that that's a desktop study I was talking about. There is not a single ocean-going seaweed farm in existence today, but there will be by the end of the year. The first array is being built off the coast of Indonesia with some money from the Australian federal government, with some assistance from DFAT. It'll be 100 square metres, it'll be exactly as I described to you, and it'll be used for marine aquaculture and for seaweed growing. 9% of the world's oceans, boy, that's a lot of seaweed going to the depths, and the depths are not just a garbage dump, yeah? The depths of the ocean have their own life forms. So as we move forward thinking about these sorts of solutions, we have to realise that we are in the very earliest stages of this whole enterprise. But the potential is there. If we want to avoid climate change, this is worth doing some serious R&D. And incidentally, the seaweed industry globally is massive and growing like that. It's incredible. I was in South Korea just a few months ago at the Wando Seaweed Expo, which is the world's biggest seaweed expo. The number of things that seaweed is used for are incredible, from surgical implants to cosmetics to food to feedstocks for animals. And it's very interesting in terms of feeding seaweed to animals. There's some preliminary data that suggests you can get massive methane reductions from feeding seaweed or shandying the feed of cattle and sheep with seaweed. So lots and lots of things. Plastics, lots of stuff being made with seaweed. Could I have... There are other scalable ways of getting CO2 out of the atmosphere. Scientists have suggested that we can actually chill the air over the Antarctic ice cap and get the CO2 out. So over the Antarctic ice cap, average temperatures are minus 57 degrees. CO2 falls out of the air as snow, it's minus 78.5. So if you put a chiller box on the Antarctic, big 100-metre cube, and had some wind turbines, you could let the CO2 fall out of snow and bury it in the Arctic ice cap. How much would you need for a gigaton per year? You'd need about half the installed wind energy that currently exists in Germany. So big, big scale stuff. This is planetary engineering, really, we're talking about now. And I don't particularly like this idea. I think of the Antarctic as the last virginal continent on our planet. But I realise that people in 2050 might think differently, that my children who are faced with the dire situation that we look like we're going to have unless we change by 2050 might want this option available to them. So let's start doing the R&D now around this sort of thing to see what is possible, what the possible adverse consequences may be, and so forth. Can I have the next? Carbon negative concretes are right here today. You can buy them in Australia. They cost about 3% more than conventional concretes, but they're there. With a few structural adjustments in the industry, they could be much bigger. They're much more like the ancient Roman concretes, incidentally, than the stuff we use today. So very interesting materials. So could I have the next slide? Silicate rocks offer a huge potential. There's some olivine at the bottom there, the ground up greenish looking rock, and a couple of research papers, early ones dealing with their potential. Could I have the next slide, please? James Hansen, one of the world's great scientists, thinks that this may be, in a way, the solution. He can see silicate rocks drawing down between 30 and 300 parts per million by 2100 of CO2 in the atmosphere. Huge impacts. The problem we face at the moment is that in order to quarry rock and to grind it up, we use fossil fuels. So until we clean the electricity system and our transport, this won't be available at scale. Incidentally, we could use silicate rocks to nourish beaches that are being eroded by rising sea levels, and that sort of thing. They can be used as a soil amendment. We can spread them widely. Direct air capture, I already mentioned, extremely efficient and already the basis of industries. In Canada, it's being used to make biofuel. Other places we are seeing direct air capture either through plants or through this chemical means as a basis for making plastics, making other materials to substitute for fossil fuels. Could I have the next slide? So there's bioplastics from CO2. Again, we've got a scalability issue. If you want to get up to a gigaton, you need to double the number of plastic bags in the world and make them all from atmospheric CO2. So no one wants to do that, but it might be part of the solution. Yeah. There is some really interesting stuff going on in this space that we're just at the beginning of. This Professor Licht here has, in the last 2 years, pioneered a new form of concentrated solar thermal technology that generates temperatures up to 900 degrees Celsius, and he's using that to break apart the CO2 molecule and to create carbon nanofibers. This is laboratory stage stuff, but so exciting. He claims he can do this at a competitive price with conventional processes. But can you imagine if you take the problem, the CO2 in the air, and make a solution out of it that competes directly with steel and with aluminium? That is powerful. Now, I know probably not the right thing to say in Wollongong, but you know, these things are very, very interesting. Just a few months after that paper came out, another one that was more amazing to me came out. Researchers at the University of South Korea have worked out how to activate used coffee grounds, again using a heat process, a CST-based process, to make a capture mechanism for atmospheric methane. This is something I'd never even thought of before. I was halfway through drinking a cup of coffee as I read this and thought I'd better have another one, you know, and realised probably, again, at scale, I'd be drinking 10 cups a day. It wouldn't really work. But it just shows you what sort of innovation is out there around getting some of this gas out of the air. Could I have the next slide, please? Artificial photosynthesis, I'm not such a fan of. Neither am I a fan of geoengineering. These are systems that they're creating something new in the Earth system, and they're band-aid solutions or dangerous solutions, I believe. What we should be following are solutions that allow us to strengthen Earth's natural processes for drawing CO2 out of the air to re-establish that balance. So important. Could I have the next slide, please? I just want to talk about timeframes because there's some young people here in the audience. You know, when we talk about 2050, as I've been doing today, we often think about it in very strange terms, either some sci-fi terms or as some version of today. Not very helpful. The way I think about it is to cast my mind back a century, to say, imagine we're in 1917, here in Wollongong. That's the sort of thing you'd be seeing. That was in London. Horse transport was everywhere. You know, your home that you would have gone back to would have been mum-powered. Electricity hadn't yet penetrated the home. Mum did all the work, and Dad perhaps a bit, doing wood chopping and whatever, but really it was, you know, done by human labour. Can I have the next slide, please? If you went to school, you would have seen a map like that. That's a map of the British Empire. That's what you would have been taught from, and that empire would have looked as immutable and unchangeable as anything on the planet. There's not a single communist country on the map, mind you. Have a look at that. Interesting, because the October Revolution hadn't happened yet in Russia. Could I have the next slide, please? So let's fast forward. Take that mindset. Horses in the street, no electricity in the house, age of empire, the war going on in Europe, and take that child, that 12, 15-year-old child, and say, now it's 1950. This is what you're seeing. Geneva, full of cars. Electrification in the home, incredible changes happening just over 33 years. Could I have the next slide, please? How would you tell someone from 1917 about jet aircraft? Could I have the next one? Or nuclear power? And yet the foundations were there. Einstein had published his theory in 1905. It was there to see if you wanted to see it, but it was unimaginable. The biggest resource we have in terms of creating a better future is our imaginations. If we say we will never get a gigaton out of the air, these are impractical solutions, we cannot do it, we will never get there. If we can just give our imaginations free rein to think about a better future and then implement it through innovation and things like this, we will get there. Could I have the... And of course, this century is seeing much more rapid change than last century, in part because we are all connected. We can move together. We have become a murmuration of human beings. You see these murmurations of birds flying through the air. This little thing in my pocket has allowed us to become a murmuration of human beings. We can work together in unimaginable ways to do things that we could never thought possible before. So that's why I'm here today, because this group of people are hugely important in terms of making that change. Thank you very much.